Hello. In earlier sessions of Practical Electronics Part 1 and Part 2, we had discussed about the functioning of the transistors. They are actually called BJT, bipolar junction transistor, but in short normally people call it transistor. We have seen how the transistor behaves and how the current flows in the base circuit in order to current to flow in the collector emitter circuit. Today we will discuss here about the MOSFETs. You see, MOSFET is also a transistor, metal oxide field effect transistor is the big name, and we call it MOSFET, MOSFET. This is denoted like this. They are available in P channel, N channel, so many other terminologies. Let's concentrate only about this type which is being displayed here. What I have done here, we have connected a load that is a 24 ohms load, that is lamp load, in series with an ammeter. Hello, in series with an ammeter, and okay. We'll zoom it again. Right. The arrangement that we have done here, we will open these switches, and these switches are open now. There are normally switches. We have a lamp and then an ammeter and a voltmeter which is connected across the MOSFET. We will see why, what is the purpose of this, and we are trying to see, because in a transistor what we have discussed, there is a current flows in the gate. Sorry, in the base. In the transistor we call it base, in the MOSFET we call it gate. This is called gate, and this is called drain, and this is called source. Okay, and just like base, collector, emitter. Collector goes to positive, here drain goes to positive, and emitter goes to ground, that is negative, and here the source goes to ground. Basically both are same, but here the drive considerations are different. What is the drive consideration? There we had seen that a current needs to flow in the base emitter circuit. Base emitter circuit. In a transistor this is called base, this is called emitter. But the picture is different. Let's not get confused over that. And here the current doesn't flow because there is a capacitor at the beginning and the gate. It just requires a voltage for this switch to get switched on. Now let's see that. So we will go over to, okay, now this is the arrangement. We will also see how the current flows. So let's go to the simulator operations. Sorry, we will set it before we go over to the simulation. Okay, we go over to the set animation options, and then we'll see how the current flows. We switch on this, and then say yes. Right, now we go over to switch on this. Now see, the same thing, the positive is here, and then once I switch on, the positive is available till this point, and there is no current flowing, though the indications are given here. There is some current flowing in the, maybe for the voltmeter, and so the entire voltage is appearing across this, entire 12 volt is appearing across this, because there is no current. We can see there is no current flowing because the gate is open. Gate is open, that means gate is already connected to ground with a resistance of 10K. Now if we have made a potential divider of 1K to 10K, that means if I switch on this, the voltage will be divided in the ratio of 1:10. So here the voltage will be higher than 10 volts. In the process, this voltage will be applied to the gate, between gate and the source. So this switch switches on. Let's see that. Right, now you see the resistance of this, what we had seen was 2.4 ohms, and sorry, it was 24 ohms resistance, we can, for the time being, supposing you would like to see the value of the resistor also, so let's go over to this. Right, so the load resistance is 24 ohms. It is 0.49 or about 0.5. So 12 volt divided by 24, because there is a negligible voltage drop across this, but we can see across the drain and the source there is a negligible voltage drop, and that is why it's about 0.21 volts across the MOSFET drain and source, and the current flowing is about close to about half ampere, that is 0.5 ampere or 500 milliamperes. Very simple. 12 volt divided by 24 is equal to 0.5. You see, there is no current flowing in the gate. It is just a voltage which was applied. This voltage, about 10.9 volt, is applied across the gate, and that is how it conducts. Right? And if I remove this, now the current stops. Full voltage is appearing across the drain and the source. So this is how a MOSFET behaves. Now the beauty is on how to use this MOSFET, and then this particular voltage drop is because of a resistance which is called RDS. That is, resistance between drain and source is called RDS. Because of the RDS, when the current is flowing, that voltage drop is appearing, and RDS varies depending on the type of MOSFET. It could be 0.001, 0.005, 0.05, 0.1, depending on the type, depending on the voltage that is available in the market, that you have to see from the specifications of the particular component. Now we will see one more interesting feature here, that now supposing I change this resistance value, which was originally 24 ohms, now let me make it 2.4 ohms. Now if I make it 2.4 ohms, now it's 2.4 ohms. So how much will be the current roughly? So 12 volt divided by 2.4 ohms. Yeah, it's about 4 amperes. The current is about 4 amperes, and there is a voltage drop which has increased from that small value to 1.82 volts. Is because the RDS, the R remains constant, and when the current of 4 ampere flows, so the voltage drop is this. You can calculate from this RDS also. Like for example, this voltage divided by this current will give you the value of RDS. Though you are not required to calculate the value of RDS, but RDS is specified by the manufacturer. The same situation you see. The current flowing is 4 amperes, voltage drop is 1.82 volts. So in certain places where we would like to see or would like to protect, what we can do, we can take this voltage drop, and since we have discussed certain comparator arrangement, we can feed this to a comparator where once the certain amount of current exceeds, obviously this voltage will also exceed. Once this voltage exceeds, because of the current exceeding, then this voltage can be fed to a comparator, and comparator can in turn take any action, that is by switching off a device or even switching off the gate current here itself, so that this itself switches off. So that is the biggest advantage of understanding the RDS of the MOSFET, so that it can be used for specific purpose. So to summarize, the transistor requires a current at its base to emitter, whereas in a MOSFET it requires a voltage from its gate to source, and it doesn't require a current. That is why the driving requirement for the MOSFETs are much better, are much simpler as compared to a transistor or a BJT, what we call normally. Thank you.